pace up, men! Get those crates secured before the next tide!
December 1941. A cold wind moves across an American proving ground. Steel shells lie in wooden crates, stenciled with neat white lettering. They look complete, finished, ready. They are not. Inside laboratories thousands of miles from any battlefield, chemists stare at chalkboards filled with formulas that refuse to cooperate. TNT cracks under pressure. Amatol burns unevenly. Shell casings rupture when they should not. Others detonate too late, or not at all. The United States is on the edge of global war, yet its artillery shells belong to an earlier era. Many were designed for peacetime testing, not sustain modern combat. They cannot be produced fast enough. Worse, they cannot be trusted once fired. In Europe, cities are already being erased by high-explosive barges measured in seconds. German guns thunder with chemical precision. British factories work around the clock, refining explosive blends for maximum effect. America watches and realizes something unsettling. It has guns, it has steel, but it does not yet have the explosive heart required to fight an industrial war. That realization will pull an unexpected force into the center of America's war effort, long before soldiers ever reach the front lines. By the late 1930s, modern war had already revealed a brutal truth. Artillery decided outcomes long before infantry ever saw the enemy. In Spain, in Poland, and across France, high-explosive shells did more than destroy positions. They shattered morale, infrastructure, and time itself. Battles were measured not only in territory gained, but in how efficiently explosives could be delivered, detonated, and sustained. Germany entered the war with this lesson fully absorbed. Its artillery doctrine emphasized rapid fire, predictable detonation, and chemical reliability. German shells used well-tested explosive fillings, TNT blends refined through years of experimentation and rearmament. British industry, battered but adaptive, relied heavily on Amatol mixtures and continuously adjusted formulations to conserve scarce TNT while maintaining destructive power. Even under air attack, British chemists refined explosive consistency, learning how small chemical variations changed battlefield results. The United States, by contrast, stood apart, geographically distant and politically hesitant. Isolationism shaped procurement decisions. Defense budgets remained modest through much of the 1930s. American artillery existed, but it was sized for a smaller, slower war. Ammunition stockpiles were limited. Worse, many shell designs had not kept pace with European developments. On paper, American high-explosive shells met basic standards. In practice, they revealed dangerous weaknesses. Some explosives were too sensitive, risking premature detonation during transport or firing. Others were too stable, failing to detonate reliably on impact. Consistency varied from batch to batch. For peacetime testing, this was tolerable. For industrial war, it was unacceptable. Reports began arriving from U.S. military observers stationed in Europe. They described artillery barges of unprecedented density, shells that detonated with terrifying uniformity, supply systems capable of delivering millions of rounds without catastrophic accidents. The implication was clear. Modern war demanded explosive chemistry as precise as engineering. Inside the U.S. Army Ordnance Department, concern turned to alarm. By 1940, internal assessments admitted that America lacked sufficient quantities of reliable high-explosive shells for sustained combat against a modern enemy. Even if factories could scale steel production, the explosive filling, the most dangerous and technically complex component, remained a bottleneck. TNT, the traditional explosive of choice, posed a dilemma. It was powerful and stable, but difficult to produce quickly in large quantities. American TNT capacity was limited. Expanding it required time, specialized facilities, and trained personnel, resources that could not be conjured overnight. Amitol, a mixture of TNT and ammonium nitrate, offered a partial solution, but it came with trade-offs: reduced power, moisture sensitivity, and handling challenges that became magnified at scale. As Europe burned through shells by the millions, the United States faced an uncomfortable question. Even if it entered the war tomorrow, could it supply its own guns? The answer increasingly was no. This vulnerability became impossible to ignore in 1940. France collapsed in weeks. Britain stood alone. American leaders watched industrial war unfold in real time, and they understood that artillery ammunition was not merely a consumable. It was the bloodstream of modern armies. Without reliable shells, guns were ornamental. Divisions stalled. Offensives failed before they began. The problem was not a lack of intelligence or awareness. It was a lack of readiness. Years of underinvestment had left America with outdated explosive formulas and limited production experience. Factories capable of filling shells existed, but they were optimized for safety and low output, not the relentless pace demanded by total war. That is where DuPont entered the story. By 1940, DuPont was already one of the largest chemical companies in the world. Its expertise ranged from industrial acids to synthetic materials. The company had long experience with explosives, smokeless powder, dynamite, and industrial blasting agents. But military high-explosive shells presented a different challenge. These were not mining charges or demolition tools. They had to survive transport, acceleration, and impact, then detonate at precisely the right moment with predictable force. When the U.S. government turned to DuPont, it was not simply asking for more explosives. It was asking for solutions that did not yet fully exist. DuPont chemists began reviewing existing formulations with brutal honesty. TNT alone could not meet projected demand. Amitol conserved TNT but compromised performance. New mixtures were needed, explosives that balanced power, stability, and manufacturability. Each adjustment carried risk. A formula that detonated two easily endangered factory workers. One that burned unevenly reduced battlefield effectiveness. Testing accelerated. Shells were filled, fired, recovered, dissected. Failures were logged without sentiment. Cracked casings. Incomplete detonations. Chemical separation under heat. Every flaw represented lives that could be lost later, either on the factory floor or at the front. At the same time, the clock was running out. In Washington, procurement schedules tightened. Contracts multiplied. Production targets were revised upward again and again. The assumption was no longer hypothetical war. It was preparation for inevitability. By late 1941, planners no longer asked if America would fight. They asked whether it would be ready when it did. Pearl Harbor would soon answer the first question. But long before December 7th, the second question had already consumed laboratories, factories, and proving grounds across the country. America's artillery problem was no longer abstract. It was chemical, industrial, human, and solving it would require more than formulas. It would require people willing to work at the edge of danger, redefining what reliable destruction meant in a modern war. Those pressures now converged inside DuPont's plants, where the consequences of failure were measured not in profit or loss, but in battlefield silence when guns were expected to speak. Inside DuPont's facilities, the war was already present long before uniforms appeared. Chemists worked under lights that never seemed to dim. Shift changes blurred. Many had never imagined their academic training would be tested by deadlines measured in casualties rather than semesters. Every formula carried risk. Mixing explosives was not abstract science. It was physical labor performed beside volatile compounds that punished carelessness instantly. Accidents occurred. Near misses were quietly recorded. Safety protocols were rewritten in real time, often after something went wrong. Workers understood the stakes, even if they never saw a battlefield. A shell that failed meant soldiers advancing without cover. A shell that detonated early meant dead hands on a factory floor. Between those extremes lay a narrow margin where chemistry had to be perfect. The pressure was not only technical, it was moral. Many chemists struggled with the reality that success meant creating more efficient tools for killing. Yet failure meant worse deaths later, caused by inadequate preparation. In that contradiction, long hours continued without applause or public recognition. High explosive shells are defined by balance. Power must coexist with stability. Detonation must be violent but predictable. DuPont's task was not to invent destruction. It was to control it. TNT remained the benchmark. It was stable under shock, safe to handle, and reliable. But it demanded scarce raw materials and slow production. Amitol conserved TNT by blending ammonium nitrate. It introduced moisture sensitivity and uneven detonation characteristics. At scale, these weaknesses multiplied. DuPont chemists experimented with adjusted ratios, binders, and casting techniques. They tested how explosives behaved after months in storage, under vibration, and during rapid firing. Heat expansion, crystallization, and separation all threatened reliability. Each improvement solved one problem while risking another. Increasing power reduced stability. Improving safety reduced effectiveness. Innovation became an exercise in restraint, finding the most lethal option that did not destroy itself prematurely. Even a perfect shell meant nothing if it could not be produced by the millions. Industrial war punished inefficiency without mercy. Factories had to be redesigned. Filling lines were reconfigured for speed. Transportation systems were hardened to prevent accidents en route. Storage protocols changed to accommodate larger volumes of volatile material. One failure could halt entire plants. One explosion could erase months of output. DuPont solutions had to survive not only firing, but assembly lines, rail cars, and warehouses stretching across the continent. Reliability became logistical. Chemistry was judged not by brilliance, but by how often it failed at scale. For artillery crews, shell reliability was life. In early engagements, unreliable high-explosive rounds produced devastating consequences. Barges fell short. Fortifications remained intact. Enemy counterfire continued unbroken. European combat reports confirmed this reality. A shell that failed to detonate was not neutral. It was a warning to the enemy. A delayed explosion disrupted timing, exposing advancing troops. American planners understood that entering war with inferior ammunition would erase numerical advantages. Artillery superiority was not about guns. It was about trust in every round fired. Axis powers entered the war with hard-earned experience. German shell production had been refined through rearmament and early campaigns. Explosives were standardized. Performance was predictable. This did not mean German technology was perfect, but it was mature. America faced the disadvantage of learning under pressure while others refined under fire. DuPont's work closed that gap, not through imitation, but through accelerated adaptation. American shells would soon meet the same unforgiving battlefield tests. There was no escaping the ethical weight. DuPont's success meant more effective killing. Yet industrial war left no neutral ground. To abstain was to fail those already committed to fight. Chemists understood that their work shaped how wars were fought, how long they lasted, and how many survived them. Precision reduced suffering. Reliability shortened battles. In that reality, innovation became a grim responsibility rather than a choice. Late November 1941, inside DuPont's production facilities, the rhythm changed. The experiments were over. The arguments about ratios and binders had narrowed to margins measured in fractions of a percent. What remained was commitment. The formulations now moving down the lines were not theoretical solutions. They were the result of thousands of controlled detonations, stress tests, and failures quietly buried in reports. The explosive fillings balanced TNT efficiency with stabilized additives that resisted moisture, heat, and shock. They could be poured, cooled, transported, and fired without betraying those who handled them. Production orders surged. Shell casings arrived by rail in endless rows. Filling lines ran day and night. Each batch was sampled, weighed, and logged. There was no time for perfection, only for reliability good enough to survive war. On December 7th, 1941, the question of readiness became irrelevant. Pearl Harbor erased hesitation. Within hours, contracts expanded beyond earlier projections. Shells that had been experimental weeks earlier were now urgently required. The United States Army and Navy demanded ammunition that could be trusted immediately, not in theory. Shipments moved west to ports and east to training grounds. Artillery units firing live rounds noticed the difference. Detonations were consistent. Patterns tightened. Failures dropped sharply. Reports shifted from concern to cautious confidence. The true test, however, waited overseas. By early 1942, American artillery entered combat zones in the Pacific and prepared for deployment in Europe and North Africa. The shells carried no signatures of their makers, only serial numbers and lot codes, but inside them were the solutions forged under industrial pressure. In the Pacific, where humidity punished poor chemistry, improved formulations held. In training exercises for amphibious landings, shells detonated on schedule, carving space where infantry would later move. Reliability was no longer a hope. It was becoming an expectation. Adjustments continued even as shells were fired in anger. Field reports returned to factories. Minor inconsistencies were addressed. Ratios tweaked. Casting techniques refined. Or compressed feedback loops to weeks instead of years. By mid-1942, the turning point was clear. America no longer questioned whether its artillery would function. The question became how much could be produced and how fast. Numbers climbed into the millions. Production lines multiplied. Safety protocols, once fragile, hardened through experience. Accidents did not vanish, but catastrophic failures declined. The explosive heart of American artillery stabilized. On battlefields, the effect was measurable. Barges became dependable. Fire plans assumed detonation rather than hoped for it. Enemy positions collapsed under sustained pressure. Artillery officers adjusted tactics, confident that shells would perform as designed. This reliability changed behavior. Commanders planned deeper barges. Infantry advanced behind predictable fire. The psychological weight of consistent explosions wore down defenders long before physical destruction did. None of this appeared in headlines. No parades celebrated explosive formulations. Yet the war quietly shifted. By late 1942, America's artillery no longer lagged behind. It spoke with industrial certainty. Each shell carried more than explosive force. It carried the outcome of a crisis resolved under extreme pressure. The turning point had passed not with a single blast, but with millions of them, each one confirming that the chemical gap had closed. And as production continued to rise, the consequences of that achievement began to reshape the war's momentum in ways that would only become visible in hindsight. Those consequences now unfolded beyond factories and firing ranges, spreading across fronts where numbers, confidence, and endurance determined victory. By 1943, the change was no longer subtle. American artillery was no longer rationed by fear of malfunction or chemical uncertainty. It was rationed only by logistics, by how fast shells could be shipped, stored, and delivered to the guns. The explosive crisis that once threatened readiness had been absorbed into the machinery of total war. Production numbers tell part of the story. American factories, fueled by revised formulations and hardened safety procedures, produced high-explosive shells in quantities previously considered impossible. Millions of rounds flowed from plants to ports, from railheads to forward depots. The bottleneck had shifted away from chemistry toward transportation and coordination. That shift alone marked a decisive transformation. Reliability followed scale. Field reports documented consistent detonation rates across climates and theaters. In North Africa, shells performed under desert heat that would have exposed chemical instability months earlier. In the Pacific, humidity no longer degraded explosive fillings at the rate once feared. The formulations held, and so did confidence. Artillery doctrine evolved accordingly. Fire plans expanded. Barges were timed more tightly with infantry advances. Commanders trusted that when guns spoke, they would not fall silent through failure. This trust shortened engagements. It reduced uncertainty. It preserved lives by replacing guesswork with predictability. The psychological effect was just as powerful. Soldiers advancing behind artillery no longer braced for gaps in fire. Enemy forces, subjected to sustained and reliable bombardment, faced pressure that eroded resistance over time. Artillery became not merely destructive, but oppressive, constant, expected, unavoidable. Behind the scenes, DuPont's role became institutional rather than emergency-driven. The company's innovations were absorbed into standardized production. Formulations were documented, refined, and shared across facilities. What began as crisis improvisation matured into doctrine. Safety, once an afterthought forced into place by danger, improved steadily. Lessons learned from early accidents reshaped factory design. Handling procedures became uniform. The explosive industry, forged under wartime urgency, emerged more disciplined and resilient. The War Department took note. Contracts shifted from short-term solutions to long-term partnerships. Chemical engineering became inseparable from military planning. Ammunition was no longer viewed as a simple product, but as a system requiring constant refinement. By the time American forces landed in Italy and later in Normandy, artillery reliability was assumed. The question was never whether shells would detonate, but how they would be used. That assumption freed planners to think strategically rather than defensively. The legacy extended beyond the war itself. Post-war weapons development drew directly from the lessons learned under DuPont pressure. Explosive chemistry advanced with a focus on control, predictability, and mass production. The industrial-military relationship hardened into permanence. Yet the human cost remained embedded in the process. Factory workers carried memories of risk. Chemists carried the weight of knowing their success translated directly into battlefield destruction. The war did not erase those contradictions, it normalized them. In retrospect, the shortage of high-explosive shells in 1941 appears as a moment of vulnerability that forced transformation. It exposed the consequences of delayed preparation. It proved that modern war punished hesitation not at the front, but in laboratories and factories long before the first shot was fired. By solving the explosive crisis, America solved more than a technical problem. It learned how quickly industrial weakness could become strategic failure, and how urgently innovation had to respond when time was no longer an ally. As the guns continued to fire across continents, the work done far from the front faded into routine. Yet its impact endured, shaping how wars would be supplied, fought, and measured in the decades that followed. And with the factories still running and the war still raging, one final question remained. What did this invisible victory truly mean beyond production charts and battlefield reports? The story of America's high-explosive shells is not a tale of a single breakthrough or a celebrated inventor. It is a reminder that modern wars are decided long before soldiers reach the battlefield. They are decided in quiet rooms where equations are tested, where failures are logged without ceremony, and where success carries consequences no one pretends to misunderstand. In 1941, the United States discovered that industrial strength without preparation is a fragile illusion. Guns without reliable explosives were symbols, not instruments. The absence of high explosive shells exposed how deeply war depends on systems that remain unseen. Chemical balance, production discipline, and the willingness to confront uncomfortable truths under pressure. DuPont's role was not heroic in the traditional sense. There were no charges across open ground, no flags raised in victory. There was only work, dangerous, repetitive, and morally complex. Yet that work reshaped the war's tempo. It allowed American artillery to speak with consistency rather than hope. It turned uncertainty into expectation. The legacy of that transformation extends beyond World War II. It influenced how nations prepare for conflict, how industries integrate with military planning, and how technology is judged not by brilliance alone, but by reliability under stress. The lesson is unromantic, but enduring. Innovation matters most when it arrives before catastrophe, not after. Today, the shells themselves are museum artifacts, rusted steel, inert fillings, silent remnants of industrial urgency. But the principles they represent remain active. Readiness is invisible until it is absent. Preparation is forgotten until it fails. In 1941, America faced that failure and corrected it just in time. Not with speeches or spectacle, but with chemistry refined under pressure and people willing to accept the burden of responsibility. In the end, the war was fought by soldiers, but it was made survivable by those who ends.